I want to make a quick video and show you how to find domain and range of exponential growth and decay functions. So we're going to start with this one. And we have f of x equals -4 times 3 raised to the negative x power. So the first thing that I look at here in this equation is the number getting raised to the exponent. So the 3 means that this is a growth because it's larger than 1. If this is larger than 1, it's going to be a growth function. So the first thing that I think about in a growth function is that it has an asymptote of y equals 0, and it looks like that. That's just a regular growth function. If this function was f of x equals 3 to the x power, that's a very rough sketch of what it would look like. Then I take the transformations a single number or sign at a time. So usually the first number I look at is this. I ignore this negative for the moment. 4 would make it stretch vertically. So if I had f of x equaled 4 times 3 to the x, the 4 would make this one stretch vertically. So instead of this, it is going to be a little bit steeper. Okay. Then I look at this negative. Now, so what this negative does, I want to come right down here. I'm going to change my color to red. So if I was to just look at the -4 times 3 to the x, the 4 makes it vertically stretch, which is this. So I'm kind of looking at this graph. This negative is going to flip it across the x-axis. So instead of this, now it flips down. Okay. And the last thing I have to deal with is this negative x up here. So that would be my final sketch of that graph. Okay, again, the 4 vertically stretched it, the negative flipped it down. This negative flips it across the y-axis. So it would actually flip it this way. And obviously that's a really, really rough sketch because that's not exactly flipped. But anyway, it gives you an idea of what that looks like. So now notice that this asymptote didn't change. Y equals 0. This line's always approaching it. Y equals 0, y equals 0, y equals 0. And the reason it's always y equals 0 is that this did not shift up or down any. So at this point in an exponential growth or decay, we can determine the domain and range. So the domain in interval notation would be -infinity to +infinity. There's no x value that I couldn't put here. This graph would go on forever and continue to go this, like the x values would still continue down that way and up this way. The range is going to go from the really small y values all the way up to the 0. So the range is really dependent upon that horizontal asymptote. You put a parenthesis there because it doesn't include 0, it never reaches that. Okay. Alright, next problem. Something that looks like this. So going through this one, we look at this number first because it has the exponent and that's a decay. So the first thing that I know this looks like is that if I just had 0.75 raised to the x power. Okay, now I'll look at this number. It's a 7. So if I just look at the 7, what that's going to do is vertically stretch it. The 7's above 1, so it vertically stretches it. And then the last thing that we have to pay attention here is the -5 at the end there. So what happens there is this -5 at the end is a transformation down, so it's going to go down 5 units. So instead of it having an asymptote of y equals 0, it would go down to -5. All the points would move down -5. And that's a really, really rough sketch. I'm not saying that's the y-intercept, it's just a sketch. So a lot of times I will sketch it this way actually, and just know, I'll make me a dotted line here and say that y equals -5 is my horizontal asymptote, which a lot of times I'll put HA. So there's your horizontal asymptote. Your domain again would be -infinity to +infinity. There's no restrictions there. And then the range, you see we don't have any of the smaller y values. The smallest y value that it gets really close to is the -5. It doesn't include -5 and then goes to the +infinity direction. Okay, let's do another one. Alright, this one here looks pretty complicated, but just take it one step at a time. The number getting raised to the exponent is 4/5, which is smaller than 1. So this is a decay function. So the first thing we know that a decay looks like is something like that. Asymptote of y equals 0. So if I was just looking at 4/5 to the x, that's what it would look like. Now, look at the 15/7. 15/7 is above 1. So what the 15/7 does is it makes it have a vertical stretch. Again, these are really rough sketches of these. This would be more curved, of course. And then the last thing we have to deal with this is +6. So if I had them all together, and then I had a +6, of course I'm changing this where this is the f of x. I'm just showing you kind of the way I get it straight in my mind. So it's going to look like this. This includes all this, but then it pushes up 6 units. So instead of y equals 0, y equals 6 would be your asymptote, and the function would look this way. So domain -infinity to +infinity, and the range would be, don't have smaller y values, 6 is the smallest it bumps up against. It doesn't include 6, and it goes to +infinity. Okay. And the next one, and final one. So when I look at this right here, I'll look at this number first. It's a growth. It's above 1. Okay. So I know I'm looking at this type of function. That would just be the 5 to the x. And then I look at this. If it is in front, it flips it vertically this way, across the x-axis. This is not negated. If this was negated, it would flip across the y-axis. When it's in the front, it flips across the x-axis. So there you go. That's that function. Domain, again, would be -infinity to +infinity, and the range would switch to -infinity because we have smaller values all the way up to the 0 but not included. Alright, so that is how you find the domain and range of just a few exponential functions.